This device was designed to hurl insults. But it's not what you think.
What are insults?
An insult is a way that let me rephrase this.
We'll explain what scientists mean by insults. But first, we need to talk about speed.
Mach is what we use to describe the speed of sound. So the speed of sound in air, if you are traveling at that speed of sound, then you are at Mach 1. Most planes, for example, fly at around anywhere from Mach 0.85 to Mach 0.95, somewhere right there. So you're just at the border. Once you go above Mach 1, you are then in a supersonic regime, so you're traveling faster than the speed of sound in air.
If you travel 5 times faster than that, or Mach 5, you're flying at hypersonic speeds. At this extreme velocity, the science enters uncharted territory.
Hypersonic conditions are particularly aggressive conditions. You have shear, you have pressure, and you have temperature, and all of these can be at extremes at the same time. It's a very hard environment for materials to survive in.
When you go over the speed of sound, you have something called a shock wave that forms. The air molecules can't get out of the way fast enough, and when you go to high enough temperatures, the air molecules start to break apart, and then they become very reactive. Either strip away material, heat up the vehicle through friction, anything like that.
Friction from the air can generate temperatures thousands of degrees Celsius. These conditions are often catastrophic.
Flight tests are expensive. We're going to have a limited number of them. And so if we want to design new vehicles and understand how these materials are going to behave appropriately, we need a short list of what we think is going to work best before we really graduate to a flight test.
So scientists at the Lawrence Livermore National Laboratory are developing ways to test materials using a specialized wind tunnel called EMIT, or Energy Matter Interaction Tunnel.
When people think of wind tunnels, they think of aerodynamic wind tunnels. So you're testing a scale model, you're testing something relatively large.
Going to a large facility was extremely expensive, very difficult to get into, and we couldn't get too close to the material of interest. Then I had the idea, why not shrink everything? Instead of large size of material, we can take a small chunk.
You're trying to understand how these materials behave, how they respond before you go build them in a vehicle anyway. And so it only needs to be a couple inches in size.
Typically, a wind tunnel, they come in different varieties. For example, you can have a closed circuit that the wind goes around and get accelerated by a fan or other means. Then you have what we call a blowdown type facility, when you start from high pressure and you go to a low pressure.
EMIT works by building up and releasing a pressure differential.
The analogy I like to use is traffic. That if you think about it, you're driving down 880, let's assume that you're lucky and you're going the speed limit for a little bit, and then there's some traffic that happens upstream. That's gonna block down the road. That's pressure, that's where you are in the chest cylinder. Then you go through that traffic jam, they've cut down the highway from 3 lanes to 1 lane, that's your throat. And then everybody has to go through that 1 lane, and then you expand back out, and everybody accelerates away. That's your supersonic expansion.
So the wind tunnel starts with a compressor. This is kind of the same equipment you'd use actually to generate high pressure air for a scuba tank. We compress just room air up to 5,000 PSI. That's our high pressure reservoir. The air then flows through a series of pipes into this main room. The flow will leave the control valve, and we'll have a go, no go valve next. Basically, it's the final, are we ready to turn on the tunnel?
The first time you turn it on, I'll always remember that day, because for me, that was actually the same as the first day that my son walked. That's a day I'll never forget.
When a test is initiated, the air is first stepped down to operating pressure and passed through a series of screens to become uniformly smooth. It's then released through a specially designed nozzle.
You can think of this similar to like a rocket exhaust nozzle. So it compresses the air into a throat, then re-expands, and when you go through this expansion is when you get the flow to go hypersonic.
The main experiment chamber is where the airstream finally encounters the test material, called a coupon. Unlike atmospheric flight, the airbursts are cold, so the material is heated by a laser source, substituting photons for friction.
I would love to believe that anytime you need to use a hypersonic vehicle, it's going to be a blue, sunny day, no clouds in the sky. But realistically, that's just not the case.
The tunnel will be able to recreate various encounters, called insults.
And so an insult then could be things like a water molecule. As it's traveling through at 5 times the speed of sound, an impact from a water molecule could damage the surface. That is the type of thing that can be an insult.
One of the most damaging insults the team can generate is shockwaves.
So if you put another sample, a sting, some sort of arm over the surface of the material, the flow will run into that and create a shockwave off the surface of that body, which you can then direct onto the surface of the material that you want to test.
So this sting for us serves as 2 roles. One is be the primary shock producer, or it can be a standalone and test a test article, in this case a cone. The opportunity to bring diagnostics so close to the material that we are testing is the most unique part of this facility.
The tunnel has viewports so that high-speed cameras can record the results of this destruction at thousands of frames per second. But cameras aren't the only diagnostic tool available. The team also uses lasers to measure stress, strain, and bending.
Lasers provide an interesting diagnostic eye into what's going on.
So we've been focusing on 2 things. That's computer-aided speckle interferometry and laser-based ultrasonics.
The surface of the material is analyzed with computer-aided speckle interferometry.
We generate a speckle pattern, or you can think of this as a random pattern of dots on the surface of the material, and we use a camera to watch that. And as the dots change, that will be due to the material changing, could be flexing, could be bending, it could be changing, transforming shape, or it could be stressing.
To peer inside the material, scientists rely on laser-based ultrasonics, or LBU.
I take a laser and I just ping the surface.
You can think of this as like a little hammer tapping the surface.
The speed of sound, a wave will travel through the material, reflect off the back, and come back out.
And we use a laser to watch how that surface changes. We can understand whether there's voids forming, porosity in the material, are we generating cracks? Because that will disturb how this wave propagates through the material.
Fluorescence and spectroscopy techniques allow scientists to measure another important phenomena: gas chemistry.
So I have my material, it gets up to several thousand Kelvin. Gas comes out of the surface, it comes out hot, and I can track that gas that's coming out and actually take measurements of that.
Chemical reactions can cause severe damage or even vaporize the material altogether, so it's vital to understand the dispersal, reactivity, and temperature of the different gases. Developing these diagnostic tools is one of the team's crowning achievements, one which they hope to share.
So we've built this as a place where if you're developing a new diagnostic, you can bring that diagnostic here and you can test it, and then you can take it to your big expensive campaign where it really needs to work.
We've gone to other offsite facilities. We were lucky to get maybe 15 to 20 runs done in a week. For us here in Emit, that's closer to a day. And the reason why that's possible is because we've sized the system to be optimized for that.
EMIT promises to be an indispensable tool for testing novel materials developed at the laboratory.
We put so much work into building out this facility. So much goes into it, and I don't know that I appreciated how hard that was going to be when I first started on the project. And the first time you turn it on was really relieving. It's a very exciting moment.
For more information on EMIT, check out Science and Technology Review.